Okay, thank you. So the next thing I'm going to talk about is, again, back to the Crete conjecture. So which domains are spectral? For which domains do we have a complete set, orthonormal set of exponentials? And as I showed you in one of the first slides, a triangle is not spectral. The same is true for every convex domain. So the theorem is that if you have a convex domain which is spectral, then it must be symmetric about some point. Usually we just translate it so that 0 is a convex number. So the only convex sets which have any chance of being spectral are the symmetric convex sets. Not all of them will be, but they must at least have symmetry. So let's start with the basic tool for this, which is the Minkowski inequality. The Minkowski inequality is an inequality that concerns the volume of so-called Minkowski sums of sets. In the particular case of complex bodies, the form which we care about is this. If you have a convex body K, and you look at its difference set, everything that you can form as K1 minus K2, okay, and you compute its volume, this volume is at least 2 to the d, where d is the dimension, times the volume of K. And the particular part that we're interested in is that the equality here is only true when K is a symmetric set. So if you start from a non-symmetric body, so this is not true, then the volume of the difference set will be strictly larger than 2 to the d times the original volume. Now perhaps I should observe here, although I'm sure you know it, that if you start with the convex body K, then the difference set is also convex. However, even if this is not symmetric, this is always symmetric. Okay? Because if you put a minus here, you get the same set. So the difference operator makes everything symmetric. So here you have a non-symmetric convex body K, and I have drawn here K minus K, which is quite a bit larger than K, right? So let's see here. The first thing we're going to prove is that in the theorem which dates back to the days of Minkowski, Minkowski proved that if you have a convex body in RD, which tiles by translation, it must necessarily be symmetric. Okay? So, in some sense, this result that I talked to you about is of the following form. That we have a property that holds for tiles, and we verify this property for spectral sets. So if you're trying to prove that being spectral and being a tile are the same thing, it makes sense to take properties of tiles and prove them for spectral sets. So one property is this, that every convex tile is symmetric. And we're going to show that every convex spectral set is symmetric. So there are many results of this type in the literature. That you have a property holding for tiles, and you verify it for spectral sets. All these results go into the direction of enhancing the validity of the Crete conjecture, which I should clarify and perhaps say a little early that the Crete conjecture is false. We now know it to be false in dimensions 3 and higher. But this doesn't mean that research has stopped, because it's known in several special cases. But by special cases, they can be quite general. One of the, perhaps the most important recent result in this business is a theorem by Lev and Matolci of 2019, who proved that the Crete conjecture is true for all convex bodies, regardless of dimension, no other conditions. If a convex body is spectral, it must be tile and vice versa. So there are important cases where the later conjecture is true. In general, it's not, and we will see why. And this is one of the theorems of what I call the prehistory of the Kolountzakis conjecture, before people knew it was wrong, so everybody was trying to prove it by theorems of this type. So let me continue by proving Minkowski's theorem. If you have a convex body K, which tiles, then it must be symmetric. So let's start with K, and translate it at the location lambda, we have a tiling, which means in particular it's a packing, so we have this ident. The intersection of the two different sets is just the zero. Now take the half body of the difference body. L is also convex, because it's just one half of a convex thing. And it so happens that L minus L and K minus K are exactly equal. This is really easy to remember. So if you take the half body of the difference body, and for its difference body, you get back K minus K. This is just a little algebra, I'm being careful. So here we have two bodies, K and L, which have the same difference body, K minus K. Well, since K minus K is L minus L, this is also a packing. Okay? Now, by the Minkowski inequality, since K is not, assuming K is not symmetric, this, okay, what does Minkowski say about the volume of K minus K? The volume of K minus K is strictly larger than 2 to the D times the volume of K. Now, if you put a 1/2 here, you're going to pick up 1 over 2 to the D here. So what Minkowski says about this case is that the body L is strictly larger than body K in volume. Both of them convex and so on. And they're both packed. Now, this is a contradiction. Why? Because in any packing of a body at those points, you must have that the volume of the body times the density of the set is at most 1. Otherwise, they don't fit. They will overflow something. But at the same time, if this is a tiling, you must have equal to 1. So from the tiling K plus lambda, you get that this times that is equal to 1, because nothing is omitted, as I explained last time. But this is not possible because L is strictly larger than K. So if you enlarge this, you'll get something more than 1, not less than or equal to 1. Contradiction. Therefore, K must be symmetric. Right? So this is Minkowski's theorem. I don't know if he proved it this way, but this is the way preferable for what follows. Let me also point out that Minkowski proved a little more than this. He also proved that if you have a convex body that tiles by translation, it must be a polytope. You cannot have any round pieces. That's really obvious. If you have something which is round, then how are you going to fill this space? Something's going to be off. So it must be a polytope, and its codimension 1 facets, sometimes they're called faces, they must be symmetric polytopes in dimension 1 mass. So for instance, in 3 dimensions, if you have something that tiles, its faces cannot be triangles, because the faces must be symmetric. Triangles are not symmetric. Okay. Now let me come to the main result, this one. So suppose we have a convex body which is not symmetric and has spectrum lambda. And let's assume for simplicity that K has volume 1. Okay? So the difference body I call here D, which is convex and symmetric, as I explained here. Now, suppose lambda is a spectrum. This is equivalent to this being a tiling at level K squared, which is 1. So this is a tiling at level 1. Spectrality is equivalent to a tiling condition, as we showed last hour. Okay? Let me call this function, the function that tiles, let me call it f. And its Fourier transform, as we have seen, is the convolution of k and minus k. So what we have here is that f plus lambda is a tiling at level 1. If you take f and you move it at the locations of lambda and you add them up, you get 1. And by the Fourier condition for tiling that we saw last time, this means that the support of delta lambda hat must be contained in the zeros of f hat. Okay? But here is f hat. What are the zeros of f hat? Well, f hat is positive at exactly k minus k. Therefore, which is a set D. Support of delta lambda hat must be in the outside of the difference body. This is the picture. So we started with a set K, which is non-symmetric. We compute its difference body, it's the big one. And the half difference body, which I call H, is now 1/2 the big one. And for lambda to be a spectrum, what must happen? The support of delta lambda hat must be outside the light green part, plus the origin. The origin is always in. So support of delta lambda hat is outside the green area. Okay. So H is the half difference body. This polygon here, this hexagon. By the Minkowski inequality, as before, the volume of H is strictly larger than 1 because K is not symmetric. Okay. Now let me take the function G, defined first on the Fourier side. How do I define it? Okay, I define it like this. Now H is, the body H, which is the half difference body, is symmetric, so I don't need to put a minus here. This is the same. So this I define to be G hat. So what is G? Is this. Okay. Now the support of G hat, which is the body H plus H, is exactly D. If you take the half body and add everything to everything, you get the double body. So the support of G hat is exactly D. Which means what? G plus lambda is a tiling. Why? When is this a tiling? If the support of delta lambda hat is contained in the zeros of G hat. The zeros of G hat contains the complement. And that's where delta lambda hat lives. Here it is. So the Fourier condition for tiling is true for this tiling, therefore this is a tiling. Okay, let me say it again. So I define a function here. First I define it on the Fourier side. On the space side, it's just a positive function. On the Fourier side, G hat lives in the green part. Delta lambda hat is outside the green part. So delta lambda hat is in the zeros of G hat. Therefore, G plus lambda is a tiling. At what level? The level is necessarily the integral times the density, always. So the integral times the density. And what is that? Well, the density of lambda is 1 because I assume my original domain at volume 1, therefore the spectrum has density 1. And the integral of G, how do I read the integral of G? For instance, the integral of G is the integral of this, by Parseval is the integral of this, which is H. So G plus lambda is a tiling at level H. But look, G is non-negative. It's this function. Let's look at what happens in this tiling at the origin. At the origin, I have at least this value. I may have other values coming from other copies, but certainly I have this. Okay? Oh, by the way, I forgot to say that almost always I translate lambda to contain the origin. That's always possible, right? The tiling doesn't change if you translate everything. So almost always we take 0 to be in lambda. So since 0 is in lambda, the value of this tiling at the origin is at least this quantity. You may have more coming from other copies of G. But from the one copy that corresponds to lambda equals 0, you get this one, which is h squared. Why is it h squared? Because the value of this function of the origin is the integral of 1h, which is h, and it's squared. So it's h squared. But h is larger than 1, which is larger, strictly larger than h. So you have a tiling where your function, at some point, namely 0, exceeds the level of the tile. And the function is not negative. That's not possible. You cannot tile at level 1 with something which assumes the height 1.1 at some point. So that's a contradiction. So what really lies behind this proof is that we managed to find another set larger than k, which has a different set, the same different set as k. That's what really happened here. We used Minkowski for this, but that's the whole, that's the plan of the proof. And it works in other cases too. So the triangle is not symmetric. Sorry, it's not symmetric, yeah, and therefore it's not spectral. So let me now come to the disk. And let's see why the disk does not have a spectrum. And this is interesting because Fugler himself said in the original paper that the disk and the triangle are not spectral, but he didn't prove either. And the triangle, I don't think there was any proof before what I showed you. There are other proofs, but not earlier. And the disk, it took a while to prove not that it's not spectral, but even stronger results. But let's start with this: the disk, and actually in dimension 2. So take the disk in the plane, and I will show to you that it's not spectral in a way which is absolutely non-extendable, not generalizable. It is if it happens by accident. So it's interesting as an entertainment value, not really as something that you can use later on, but it will also help us to digest some geometric notions. So let's start with the set D, which is the unit area disk in the plane. So the radius is 1 over root p. Now, if we take the function, the indicator function of D, these are nice charts, but very sensitive. If you take the indicator function of D, this has rotational symmetry. This passes on to the Fourier side. So both this and that have rotational symmetry, which means that the zeros of this guy are full circles around the origin, like this. It just so happens that we know, in a sense, what those zeros are. There's a so-called Bessel function of first type, and this is essentially that one, up to constant multiplicative constant. So these zeros have been studied a lot, but even if they have not been studied a lot, it's very easy to numerically get some information about the zeros. And what matters is the first zero, which I call here R0. So R0 is the first circle of zeros in that function. Certainly, you cannot have arbitrarily close to 0. Okay, you cannot have such circles arbitrarily close to 0 because your function is continuous. It would vanish at 0 if you had circles arbitrarily close to 0, but its value at 0 is the area, it's 1. So there is a finite number, R0, where the first 0 shows up. Okay? Suppose it's spectral. So suppose we have a spectrum, and then, as we remember, for two frequencies to be orthogonal, we must have that the difference lives in the zeros of the Fourier transform. So, lambda minus lambda should be contained in the zeros of this function. That's equivalent to orthogonality. Okay. So the zeros of 1D hat is a collection of circles, a certain radii are 0 or 1, and so on. The first guy is 1.08, and so on. You can either look it up in tables of the Bessel function, or you can numerically approximate. Now, what happens if we place a disk of radius r0 over 2 around every point of lambda? So the point of lambda, say lambda 1 here, lambda 2 there. This distance must be one of the rj, either r0 or 1 or 2 or so on. r0 is the smallest one. If I put a disk around each lambda of radius r0 over 2, then these disks are non-overlapping. Why? Because for two disks to overlap, the sum of the radii must be at least this distance, but it doesn't happen. Even for the smallest distance, it's exactly equal. So we have non-overlapping disks, like that. So assume we have a spectrum, then it must be the case that if I place a whole disk of radius r0 over 2 around each point of the spectrum, these are disjoint. Now, this situation which I have drawn there is what we call a disk pattern. This is a subject that has been studied quite a bit. So you have as many copies of the same disk as you want, and you place them on the plane in a non-overlapping way. What is the higher density you can get? You can certainly not get 1, because you cannot achieve complete covering with non-overlapping disks. That's obvious. But how much can you get? Well, this is the theorem of 2a, perhaps more than 100 years ago. The density of any disk packing in the plane, being equal disks, okay, is at most, you can at most cover p over root 12, which is about 0.906 and so on, which is already quite big in my intuition. You can get at most that. This is 2a's result. All right. So what do we have? Well, we have that our density of our lambda is 1, because it's a spectrum of an object of volume 1. So what is the density of this packing? To find the density of this packing, you multiply the density of the locations times the mass, the area of each object. The area of each object is this. Do the calculations and get 0.917 something, which happens to be larger than that. So it contradicts 2a's result. This cannot happen. So the disk is not spectrum, it's not spectral, because if it were spectral, it would contradict the largest possible disk packing. Now, this does not extend to higher dimensions. Okay. Not to mention the fact that up until some years ago, the best ball packing in higher dimensions were not known. This is the Kepler problem. Anyhow, let's now do not just the disk, but any smooth convex body. The disk certainly is a smooth convex body, as is the ball in higher dimensions. Let us prove why a convex body which is smooth and symmetric, it must be symmetric, we prove this, why it cannot have a spectrum. Okay. Now if you have a body K, which is symmetric and convex and smooth, it has long been known. People were studying this stuff in the 30s or 40s using the stationary phase method when they're trying to estimate the number of lattice points contained in multiples of a ball, say, or a large convex body. People have studied the Fourier transform of this function in detail, and we know more or less where the zeros are. What do I mean by more or less? First of all, we know that the zero, if you fix any straight line out of the origin and you go out like that, you will encounter zeros, a discrete set of zeros, necessarily, because it's an analytic function, a discrete set of zeros, and as you go out, it's an asymptotic result, as you go out, these zeros will be coming regularly, almost after a constant each time. And we know what the constant is. as long as we measure things in the right distance. So what is this object here? Every convex body has a polar convex body. This notation here is the norm defined by this convex body. We all know what a norm corresponding to a convex body is. So for the Euclidean norm, the convex body is the sphere. But you can have an ellipsoid, which will give you something like a Euclidean norm of preferential directions. You can have a polytope, convex polytope, which will give you another norm. Here, the asymptotics which are known about the zeros are usually expressed in this norm. So if you take a point C and you let it go to infinity, you either consider this norm or that, doesn't matter. Then the K0 norm of C, okay? The K0 norm of C will be approximately this constant, there's no K here, plus an arbitrary integer multiple of P, plus something goes to 0. It's a very precise result. It tells you that if you go up and you measure lengths in this sense, your zeros come almost regularly. The method to prove this is a stationary phase. People have done this in minute detail for many, many purposes. A few more words about the polar body. If your original body K looks like this, the polar body is somehow elongated in the directions where your original body is narrow, and narrow in the directions where your original body is long. So if this is the original body, then the polar body will be a dilate of something like this. That's why I've drawn here. These red lines are the zeros of 1K half. And as you go out, this shape will look more and more like a dilate of the polar body of K. Okay, this is what we know. You can find, of course, the same result expressed without this name, different, but I think this is the best. And how do we use it? Okay, again, there are many proofs of this. The proof which I'm going to give you is mine, and I think it's one of the simplest proofs that exists if you assume the right set of tools. And the right set of tools here is a result in geometric Ramsey theory. I have listed here several authors. The most general result is by Duguin. This is my tribute to Belgium here. Furstenberg and Seltzer and Weiss had an ergodic theory proof in dimension 2. Duguin proved it in all dimensions, and he also proved more. Both these two papers consider the Euclidean distance of what I'm going to say. I did the general case for convex bodies, which is what we use here. What does this say? This is a theory. If you have a set E in Euclidean space, which has positive upper Lebesgue density. Okay, let's explain this. What is positive upper Lebesgue density? It means that there is a constant C such that there are arbitrarily large, let's say R, and there are locations in RD, such that if I measure the volume of my set in this cube, so I take my set, I look how much of it is in this cube, I measure it, and I get larger than C times the volume of the cube. Okay, this expression, this means that my set E has upper density. Upper means that I can choose where I will measure it. Upper density, which is positive, at least C. There are arbitrarily large regions of space where my set takes up a constant part of the space. There might also be regions of space where it's empty. I don't care. I just want that I have large regions of space where my body takes up a good fraction of it. If my set has this property, says the theorem, then I can find all possible distances in there. Okay, for any distance I can choose to look at here. Not any, there are some exceptions, but certainly for smooth convex bodies, there's no issue. In the Euclidean setting, what does this say, which is more familiar? If I take any such set, then there is a length L0, so that for every length more than that, I can find 2 points of my set with distance exactly L. All large enough distances are implemented in my set. This is what it says. That's why it's Ramsey theory. Ramsey theory means you start with something which is big and you extract some structural properties. The structural property here is that we have points at a certain distance. And what I did in this is that instead of talking just about Euclidean distances, I allowed to put any convex body here with not too few sides, if it's a polytope or any smooth convex body. And how do we use this to prove that K, being a smooth convex body, cannot be spectral? Okay, we're using in the following form that if instead of talking about sets of positive Lebesgue density, we take a point set lambda of upper counting density. What's the counting density? You're going to have lambda here, but you're not going to measure Lebesgue. Measure, but number of points. Right, it's points. So if you
come back,
sorry.
What a lot.
The button
Wow.
is pressed. Yes.
Here.
Yes.
Okay. So if you start with a large set of points of positive density, then you cannot, of course, hope that this set will implement all distances. After all, the distances implemented by this are a countable set. You cannot implement everything. But you can hope that you will get epsilon close to any distance you want. So, and that actually happens. It's very easy to reduce this to that. How do you do it? You start with something of positive counting density. You add a epsilon ball at each point. It becomes a set like that. You apply your theorem. You get points with the exact density. Then you move to the nearby lambda points and you're going to lose epsilon. That's it. So whenever you have a separated set of positive density, you're going to get close to any distance you want. But if lambda is a spectrum of this convex body, and I measure distance in this metric, then all the differences, because they must be part of the zero set, must look like this. So this is a constant plus an integer plus something tiny. So if you look at those distances on the line, it will look like an arithmetic progression and epsilon close to that. These are the distances in that metric. Well, certainly you cannot come close to such a number. Okay? So since these interpoint distances are not in some sense dense in the line, they are quite separated, it contradicts this thing. So smooth convex bodies do not have a spectrum. Okay, now I don't know if it's wise to start this one because this is perhaps the most technical part. Perhaps I will skip to the end of this and give you some other background results. Okay, so let's do the quick thing again. Okay, here we are. So the disk I will talk about tomorrow. So let me give you some results that are known. This list is not exactly up to date. The last couple of years are missing, but I have repeated several of those results speaking. So, regarding the Fugletti conjecture, one direction of the Fugletti conjecture, the convex, for convex set, tiling implies spectrum, was known for ages. Why? Because people like Benkov and McMullen had proved that any convex set which tiles by translation can also tile by lattice translations. they have proved structural results. I mean, these are polytopes. Convex stacks with tile are polytopes. That's the first thing they proved. And then they proved structural results about those polytopes. So they have this many number of faces. Their faces are symmetric. And this structural result allowed them to construct a lattice with which they actually tile. But we know the lattice Fublet is true. So if you have a convex body which lattice tiles, then it also has a lattice spectrum. Therefore, any convex tile, since it's also a lattice tile, will have a lattice spectrum. So this direction was known to begin with. It's only 3 years ago that the other direction was proved. In full generality, by Lev and Matolchi, proved that any convex set which is spectral is a tile, and therefore also a lattice tile. Now this is my result that I just described to you. No, yeah, the previous one. Okay? And this is the result that I talked to you about. And this is not my proof. It was proved by Josevich, Katz, and Tao in 2001, using quite different methods. So they proved that no convex body, which is smooth in RD, in fact, they had a little less than smoothness, can be spectral. And they also proved the conjecture for convex bodies in the plane, only in the plane. Now, in the plane, if you have a convex tile, it must be either a parallelogram or a symmetric hexagon. There are no other convex translation of the tiles. Nothing else which is convex can tile by translation. So, what the Josevich, Katz, and Tao did is to prove that if you have a parallelogram, which is the easy case, or a symmetric hexagon, which is spectral, and it must also be tile. Or if you have any, I'm sorry, I didn't say it correctly. If you have any convex polygon in the plane, which is spectral, it must be a parallelogram or a symmetric hexagon. Therefore, tile. That was a very strong indication that the conjecture would be generally true, but it turned out not to be. Here's another result of mine, which resembles very much the non-symmetric case, but it's not restricted to the convex case. It's about polytopes only, and it says this. Okay, suppose I give you a polytope, and I claim this polytope can tile space by translation. Could it ever look like this? Could it ever have a side this way and a side that way, which are parallel? One looks this way, one looks that. There's no other side looking in that direction, and they're different. It cannot be. Why? Let's understand this. So suppose this tile. Imagine the plane covered with copies of this guy. Okay, something must come and face this side A. The only thing that can face here is copy of B, and vice versa. Right? So overall, the total length of the A's you have must be equal to the total length of the B's you have, because each must counter the other in the tile. But this cannot happen, because this is length 3 and this is length 1. So no matter how many copies you have, you will always have 3 times as many A edges than B edges. The B edges are never enough to counter the A edges. So the only polytopes that can tile must have, in any normal direction you choose, they must have the same area looking this way and that. Actually, for convex polygons, this is equivalent to being symmetric because of the uniqueness of the so-called Gauss map. If you take any convex, say, body, and you map it, you map every point of the surface to the corresponding point on the unit sphere where its normal says it should go, then you got the Gauss map. It gives you a measure on the sphere, and if you have a Gauss map which is symmetric, then the original body is symmetric. Okay, but this is not exactly available here. What we proved here is that if you take any polytope which is spectral, and you look for every normal direction, how much length looks this way and how much length looks that way, it must be equal. Exactly as happens with the tiles. This is also a theorem of the type. If something is true for the tiles, it's true for the spectral sets. Okay? Here's another old theorem. If you have, this is in one dimension, if you have a set of length 1, which lives from 0 to a little less than 3/2, so it's a kind of compressed set. So you give it almost 1.5 length, and you have total length 1 in there. It's kind of tight. Then, for such sets, a conjecture is true. A very specialized result. Probably completely uninteresting by now, but still, at the time, it was one step forward to the edge of the cliff, because conjecture proved to be false. Then, it was proved to be true for 2 intervals by Lava. The tiling to spectral part was proved for 3 intervals, and it's still not known in the other direction. We still don't know if a union of 3 intervals of the line, which is spectral, must be tiling. This is a really annoying thing, because I'll tell you later why it should be known, but no one has managed to do it. I have myself tried, of course, but I haven't been able to do it. Okay, let's now come to the point where the conjecture was proved to be false. In 2003, by Tao. How much time do I still have?
Like 20 minutes.
15 minutes.
Okay, fine. So why is it true that it fails? First of all, we must understand why the conjecture makes sense, not just in Euclidean space, but also in all sorts of abelian groups. So I should say a few words before proceeding with Tao. So suppose you have a group G, which is abelian, and the most general setting is what we call locally compact. Now, a subset of this category, of course, is the finite groups, finite abelian. They are completely compact, not just locally. The locally compact groups are the Euclidean spaces, the integers, and so on. Okay, why does the conjecture make sense in all these groups? For every such group, we know we can associate to it the group gamma, the group of characters. A dual group, as we call it. Well, what are the characters? These are the complex exponentials in general, the homomorphisms to the complex numbers. And the dual group of the dual group is the original group, that's Pontryagin duality. And what is Fourier analysis on G? It means express everything as a linear combination of characters. The characters, the elements of this group, will be functions from G to the complex numbers. If you take any function here and you express it as a linear combination of those, you have expressed it you have written it as in a basis. And you can show that you can do orthogonal Fourier analysis using those. So what is the general statement of later? And I will now restrict myself to the finite abelian case, not because it's not true here, it's just fine, but it makes things much more concrete and easy to express in the finite case. So suppose from now on that G is a finite group. How do I express spectrality? I have a domain omega in G. And what is the question? Is there a set lambda in the dual group such that if restricted to omega, it becomes an orthonormal or orthogonal set of functions, complete in omega. Now everything is finite here, so it's just about the number. If you can find, these are linear they have to be linearly dependent on omega and complete. But completeness is something in the finite case that you only need to check their number. So again, if lambda and mu are two characters, what does it mean for them to be orthogonal on omega? It means exactly, look at the Fourier transform of omega, which is now a function on this group. Have lambda minus mu, and it has to be 0. I do not want to repeat the calculations, they're exactly the same. Doing growth. So again, orthogonality means that lambda minus mu is in the 0 set. And since I have a finite, in the finite setting, I just need to find lambda 1, lambda 2 through lambda omega, as many guys as this says, in order to have completeness. If you're going to express every function of omega, and omega has 10 points, you're going to need 10 functions. So that's what spectrality is, and the condition is again the same as before. You take the Fourier transform of omega, this is a function in gamma, you square it, you translate it by a location of lambda, you should get this number everywhere on gamma. Everything is the same, and even simpler in this function. So what did Tau do? Tau found a finite where the conjecture fails. And then he somehow pulled up the result from the finite group to a Euclidean space. He could only get it up to r to the 5th, but then people got it down, and it's now known in dimension 3 and higher. Both directions of the conjecture fail. In dimension 1 and 2, nothing is known. So it could conceivably be that the conjecture is true in dimension 1 and 2. I don't believe it, but it could be. So let's see Tau's example. So in which group did he work in? He worked in such a group. Now these are cyclic groups of length n1, n2, nd. And he constructed an example here. What do I mean by an example? I mean a domain omega, which is spectral in a sense, but does not tile the group. And then he found a way to lift this example first to ZD, which is also a locally compact abelian group. D is the number of terms here. And then from ZD, that was easier, just adding a little box next to each point to RD. But the interesting thing is what the example is. It was so ridiculously simple that the group of us who were doing results in the positive direction of Atlantic conjecture sort of kicked each other for a while. It was extremely simple. Let's see. Okay, so first of all, he chose all the n1, n2, nd to be 2. So the group he looked at is z2 to the n. It's a cube. What are the exponentials in this group? Essentially minus 1 to the n, and 1 minus 1 to the n2, and so on. And he took this specific set in this group. What is E1? E1 is the vector 1, 0, 0, 0, 0. E2 is 0, 1, 0, 0, 0, and so on. So he took those n points as your set. Now, if you consider... Okay, I need to do this on the board. So you have n points in that group, and the characters on that group are of this form. It's minus 1, so let me write gamma, I should index it by. All finite groups of this type, their dual group is itself. So the dual group of z to the n is also z to the n. So the index I should put here is just a subset, essentially. It's a subset of, say, 0, 1 square. So this applied to x, where x is an element of this group, looks like this. Okay. Now, if X is one of those sets, about those points in the group, so gamma S of Ej would be -1 to the jth coordinate of S. So it's going to be a plus or -1. So if I list the characters in the spectrum as rows and I put E1 through En as columns, what I end up looking at is an n by n matrix of plus minus 1s. And what do I want? I want every 2 rows, so the rows are the characters, these are the points. Every 2 rows to be orthogonal, which is the same as every 2 columns to be orthogonal. There's a name for such thing. The Hadamard matrix. So basically, for a spectrum to exist for this set, it's if and only if Hadamard matrix exists. And Hadamard matrices do exist. Not for every n, we don't still know for every n, but for n equal 12. They do exist. You can even write it down. So for n equal 12, omega is spectral. But it's a set of size 12. 12 does not divide 2 to the 12. You cannot possibly tile that because there's a 3 in 12. There's no 3 in the group. So you have a spectral set which cannot tile. And then he uses the machinery which I described in the first lines to pull it up to r to the 5th. But the real work is this matrix. To observe that on that group and for that set, spectrum is the same as Hadamard matrix. So do I have a Hadamard matrix? No, I have a spectrum. And then you observe that for some n, like n equals 12, n does not divide to the n. And after that, less than a year after tau, so tau, this group disproved the conjecture in this direction. Spectral implies tiling. This is what tau did. But it could be that the other direction was true. We disproved this, myself and Martin Matolci in 2004. We disproved this also in dimensions 5 and larger. Now, I must say that this proof is much harder than Tau's proof. There is no corresponding criterion for non-spectrality than the one we use for non-tiling. For non-tiling, if your size does not divide the group, there's no way you can tile. There's no such criterion for spectrality. We had to work a lot harder. But we made. And again, for dimension d equals phi and more. And then people, Matolci was visiting me in Crete over the summer. If you went back to Hungary, he let other Hungarians know about it, and they reduced the dimension to 3. And also, myself and Matolci had also reduced Tau's dimension to 3. And now the conjecture since 2004, maybe 2005, is still open in both directions for dimensions 1 and 2. I don't know what follows from here. I think I should stop and leave the rest for tomorrow. Yeah, I don't want to go there. So, I think I'll stop.
Thank you. Any questions?
I have one. If we consider a lattice on a planet, if I want to count the lattice points in a given shape, is there a possible relation between the concentration function and the size of packings or tilings?
So you have a convex, let's say convex
Yeah.
set, and what we usually do where we count like we either inflate it and you look at the asymptotics or you look at precise numbers. Perhaps the second is more relevant.
For the
to time.
behaviors.
So if you wanted to lattice tile with that lattice or with a sublattice of that, then something must be true about something specific must hold. Otherwise, it's not going to happen. But if you have a general, if you ask the tiling conjecture in any tiling complement, then you cannot say anything. You must restrict yourself to, so you're looking at lattice points of lambda, and you also want to consider tilings with lambda. Otherwise, you cannot connect the two. And then I think the best thing you should do is look at Pick's theorem, where you have, say, a common polygon, and you count the points in the interior with 1, the points in the faces, but not on the vertices with 1/2, and then on the vertices you put 1/4, I think, and then you prove that this quantity, this way to measure count lattice points, is probably equal to the area or something like that. And you can connect this to lattice tilings, or by sublattice rather, lambda, but I cannot give you something more specific, but surely there's a connection.
Thank you.
Any other question?
So this is, of course, difficult problems, but I'm just wondering if you introduce some curvature, for example, if you try to tile the sphere or hyperbolic planes and some speciality, one can find a suitable node.
Yes, I mean, you see, I have a disadvantage. Whenever things become non-commutative, I give up. So if you try to tile something where the corresponding Fourier analysis is not the one I know, which is the ordinary Fourier transform, and starts involving representations or things like that, I tend to give up. So I understand it's a drawback of mine. I have to live with it. You don't have to live with it. But certainly the questions have corresponding analogs in the non-commutative case. It's just that I have not ever tried them seriously. There are some papers, there's even a paper by Alex, I think, where they have a very nice question posing about the sphere. I can send it to you.
Okay, thank you. We can discuss anyway with Professor Kolountzakis until 6 o'clock when we have the floor, right? At 6:30, where is the in the garden, like?
In the garden.
Garden section on Wednesday?
So please.
Okay, so thank you again.
Thank you.
I think it is